Welcome to the next class of data communication network. So in our previous class, we were talking about error detection. We tried to discuss a concept called Hamming distance. What do we mean by minimum Hamming distance? And then we discussed about two different error detection techniques called simple parity check and two-dimensional parity check. The simple parity check is a simple one bit or odd number of error bits detection technique, whereas a two-dimensional parity check can detect up to 3 errors and can help in correcting up to 1 error. So in next class, we'll start with the next method of error correction called Hamming code. Okay, so let's start the discussion. The Hamming code is one of the error detection and correction technique with a minimum Hamming distance of 3. So in our last class, we have discussed one of a logic related with Hamming distance and error correction and error detection is number of the minimum Hamming distance d minimum for error correction should be equal to, so d minimum for error correction is 2s plus 1, and in case of error detection the minimum distance is s plus 1, where s is number of bits of error can be detected in the second case. In the first case, s refers to number of errors that can be corrected. So if I want to detect one error, the minimum Hamming distance should be 1 plus 1 equal to 2. But in case if I want one bit of error to be corrected, the minimum Hamming distance required is 2 into 1 plus 1, 3. So Hamming code is having a minimum Hamming distance of 3, so it can correct up to 1 error. We can correct up to 1 error using Hamming code. Now here we need to find the relation between the length of code word n, data word which is represented with k, and the number of redundant bits which is here equal to the minimum Hamming distance em. Okay, so what is the relation between n, k and m? First, to determine the length of code word n, the relation we have to use is 2 power m minus 1, where m stands for the minimum Hamming distance. So in this case, we are taking m equal to 3, then the value of n equal to 2 power 3 minus 1, which is equal to 7. So once you know the value of m and n, the value of k is determined by using an equation called k equal to n minus m, which is 7 minus 3 equal to 4. So the value of n equal to 7 and the value of k here is equal to 4. So n equal to 7, k equal to 4, and number of redundant bits r is equal to the minimum Hamming distance equal to m, which is equal to 3. So I hope we know all the three values which we are going to use in our calculations. So Hamming code with a minimum Hamming distance of 3 is able to correct one error and can detect up to 2 errors. The length of code word for m equal to 3 is 7 and length of data word is k equal to 4. Right? Okay. Now let us take a simple example which is shown here with the length of data word k equal to 4 and length of code word n is equal to 7. So when your data word is of length 4, what are the total possible combinations? 0, 0, 0, 0 to 1, 1, 1, 1. So totally you will have 16 different possible combinations with 4-bit length of data word. Now we'll represent all those 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So starts from 0 up to 15. So these are the possible data words. Now for this 4-bit data word, as we have discussed in the previous slide, the length of code word n is 7. So that is what we are representing with Hamming code 7, 4. Right. So 0000 is indicated with 7-bit code word, all zeros. Similarly, 0001 is indicated as 0001 and 101. So we have different code words possible for the possible data word combinations. Now everyone got worried about how did I get this code word for a given data word. We will be discussing that in our next slide. So I hope we are clear with the instant like. For an 4-bit data word, the length of code word is 7 and number of redundant bits which we are indicating with pink color is 3. Okay, so the 3 is also equal to minimum Hamming distance. We have it out. Let us check two nearby code words. The first code word for 0 and 1 could find they are differ by 3 bits. So if two code words differ by 3 bits, what is the Hamming distance? It is equal to 3. So that is what we discussed in the. So you try to check different code words and you will find the Hamming distance between those two sets will be either 3 or greater than 3. Okay. So how do we determine the value of redundant bits for the given data word? For instance, we have taken a data word of 4-bit length, which we are indicating with alphabets A3, A2, A1, A0. Now for this 4-bit data word, the length of redundant bits is 3 because we have taken minimum Hamming distance m equal to 3 and n equal to 2 power 3 minus 1 equal to 7 and 7 minus 4 is 7 minus 3 equal to 4. Okay, so 3 redundant bits are to be generated so that we can add those 3 redundant bits to the given data word and convert it into a 7-bit code word. So what is the code word we are expecting? A3, A2, A1, A0 along with 3 redundant bits R2, R1 and R0. So this code word will be transmitted to the receiver end and the data received at the receiver is indicated with the variables. So instead of A, we are representing with B and the 4 data words bits are represented as B3, B2, B1, B0 and the redundant bits are indicated with variables Q2, Q1, Q0. Once we are receiving data at the receiver, the next thing we try to do is we forward this received code word to the checker circuit. And checker circuit will perform an operation called calculation of syndrome. So here the checker will be calculating the value of syndrome and the syndrome is of 3 bits similar to the redundant bits. Now syndrome is indicated with the variables S2, S1 and S0. Once the syndrome value is calculated, we are applying that syndrome value to the correction logic. In correction logic, we have certain rules to be followed. What is that? If the value of syndrome S2, S1, S0 is 0, 0, 0, then the data will be accepted. If syndrome value is 0, 0, 0, then let me draw this. If syndrome value is 0, 0, 0, we are going to remove the 3 redundant bits and will be transmitting those B through B2, B1, B0 as data word A3, A2, A1 and A0. In case if syndrome is not equal to 0, if it is not equal to 0, then it indicates there is an error in the transmission that has to be corrected. Okay, if it is not equal to 0, an error is generated in the transmission. Now, where is the error? How do we, whether this technique is forward error correction where receiver itself will do the correction or it will be asking for retransmission? Actually, the Hamming code is a forward error correction technique. So the receiver itself will try to determine where the error is and then tries to rectify the error and forwards the corrected data. Now how that happens, let us look for the next slide. I hope before that this is clear. First we'll take the data word, then we'll calculate the redundant bit values for those data word and transmits data word and redundant bits together as a code word. At the receiver, the received code word is forwarded to the checker. Then we are going to calculate a syndrome, and the value of syndrome is applied to the correction logic. If the value of syndrome is 000, then it is data is correct and it will be forwarded. By removing the redundant bits, we'll extract the data. If the syndrome is not equal to 000, then an error has been present and we have to correct that particular error. Pardon. Okay. So let's we go for the next one. Right. So here we are talking about a data word, and then we are trying to determine the code word for that by calculating three redundant bits. For instance, our data which we are transmitted was A3, A2, A1, A0. So the data which we are transmitting is A3, A2, A1 and A0. So this is my data word which I have to transmit to the receiver. For this I have to add three redundant bits called R2, R1 and R0. So I am taking a data called 1 represented in 4 bits, like 1 in 4 bits is represented as 0, 0, 0, 1. So this is my data which I have to transmit. So A3 is 0, A2 is 0. So this is A3, A2 is 0, A1 is 0 and A0 is 1. So for this 4 bit of data word, we need to calculate the R2, R1 and R1. So what is the process of doing is we have to implement modulo addition. What are the rules of modulo addition? 0 plus 0, that is nothing but an exclusive OR. 0 plus 0 and 1 plus 1 is equal to, so modulo sum of same bits. Two input bits are same, the modulo sum is 0. If two bits are different, okay, let me continue in the next one. If it is two bits are different, that first bit is 0 and second bit is 1. At the same time, first bit is 1 and second bit is 0. The modulo addition of these two is 1. So we need to implement the modulo 2 addition of the respective bits. Let's start with this. R0. R0 is equal to modulo 2 addition of A2, A1 and A0. What are A2, A1 and A0 here? A2 is 0, A1 is 0 and A0 is 1. So let's start modulo addition. First A2 0, modulo 2 addition with A1 0. 0 modulo addition with 0 is 0, and the resultant 0 modulo 2 addition with 1 is 1. So R0 here will be 1. I hope you got this. So simple. Instead of plus, we'll try to represent it with modulo 2 is nothing but exclusive OR operation. This is the reason why we have introduced modulo 2 addition in the beginning of this chapter. So 0 exclusive OR with 0 is 0, 0 exclusive OR 1 with 1. Similarly, what is R1? A3 is 0, A2 is 0, A1 is 0. So here let me put A3, A2, A1 and A0. So 0 exclusive OR with 0 is 0. 0 exclusive OR with 0 is 0. So R1 value is 0. Next, R2. R2 we can determine by modular sum of A1, A0 and A3. Let's look at the logic behind. First we are R0 we are starting with last 3 digits A2, A1, A0. For R1 we are taking A3, A2, A1 and for R2 we are taking A1, A0 and A3. So for this A1 is 0, A0 is 1, A3 is 0. 0 exclusive R1 is 1 and 1 exclusive or 0 is 1. So here we are going to get R2 equal to 1, R1 equal to 0 and R0 equal to 1. So what is the total data going to be transmitted? A3 0, A2 0, A1 0, A0 1, R2 1, R1 0, R0 1. So if your data to be transmitted is 0001, then it is converted to a code word called 0001 101 and it is going to be received by the receiver. Okay. Now at the receiver, what is the data that we are going to receive? We have just seen the previous slide, that is B3, B2, B1, B0 and here R2, R1, R0 is indicated with the variables Q2, Q1 and Q0. So I am going to receive data as a 7-bit code. For instance, here I assume whatever the data that has been transmitted by the sender is received as it is by the receiver. There is no error generated during the transmission. Now, how do I determine whether there is error or not? As I mentioned you, we have to calculate the syndrome value from the code word received at the receiver. How do we determine the values of syndrome S2, S1 and S0? So let us follow the same logic. For S0, the modular addition bits to be considered are B2, B1, B0 and Q0. What is B2, B1, B0 and Q0? Let me just put it here. B3, this is B3, B2, B1, B0, Q2, Q1 and Q0. So these are the code word that we have received. Now from this 7-bit code word, we have to determine the syndrome values S2, S1 and S0. Let us start with S0. What is the formula of S0? Modulo 2 addition of B2, B1, B0 and Q0. So what is B2? 0. Exclusive OR with B1 is 0, B2 is 0, B1 is 0, B0 is 1 and Q0 is also 1. So 0 exclusive OR 0 is 0, or you can say it as 0 mod 2 addition with 0 is 0, 0 mod 2 addition with 1 is 1 and 1 mod 2 addition with 1 is 0. So the value of syndrome is 2 equal to 0. Similarly B3, B2, B1. What is B3 value? 0. B2 is 0, B1 is 0, and Q1 is 0. So 0 mod 2 addition with 0 is 0, 0 mod 2 addition with 0 is 0, 0 mod 2 addition with 0 is 0. So S1 value is also 0. B1, B0, B3, Q2. B1 0, sorry, right, B1 0, B0 1, B3 0, and Q2 is 1. So 0 mod 2 addition with 1 is 1, 1 mod 2 addition with 0 is 1, 0 mod 2 addition with 1, let me just correct it, 0, B1 is 0, B0 is 1, B3 is 0, and Q2 is 1. So here what happens is 0 mod 2 addition with 1 with 1, 1 mod 2 addition with 0 is 1, 1 mod 2 addition 1 is 0. So here you will get S2, S1, S not equal to 0. When the syndrome bits are S2, S1, S0 is equal to 0, it indicates there is no error generated in the transmission and whatever the data we have received is correct. I hope this is how the calculation has to be made. We'll try, I have made you people to try one simple example of 0001. So I expect you to do a small problem like when I transmitted data called 10, which is represented in 4 bits like 10 is represented with 1, 0, 1, 0. You people need to determine the value of redundant bits for this R2, R1, R0, then transmit it to the receiver, and then along with this 4 data word bits, you have to add R2, R1, R0 and try to verify if error is generated or not. This you have to do as a practice. Right. So here, now in case if you find the data word which is transmitted is 0, 1, 1, 1. So if I am trying to transmit data 0, 1, 1, 1. And I need to find out my redundant bits. So these are my A3, A2, A1 and A0. Okay, so if the data to be transmitted is 0, 1, 1, 1, then how it is going to be transmitted? First, we need to find out the value of R2, R1 and R0. So first we have the formula for R0, which is nothing but R0 equal to A2 plus A1 plus A0. So we'll try to determine the value of R0. What is that? A2 is 1, A1 is 1 and A0 is 1. So all 3 bits are 1s. So 1 mod 2 addition with 1 is 0 and 0 mod 2 addition with 1 will be 1. So the value of R0 is 1. Similarly, what is the formula for R1? R1 is A3 plus A2 plus A1. A3 plus A2 plus A1. Now what are the A3, A2, A1 values? A3 is 0, A2 is 1 and A1 is 1. So when you do the mod 2 addition of these 3 bits, you are going to get, yes, what we are going to get? You are going to get 1 mod 2 addition with 1 is 0. Similarly, R2. What is the bits to be considered for the R2? It is A1 plus A0 plus A3. So what are A1 1, A0 1 and A3 is 0. So if you do the modulo 2 addition of these 3 bits, 1 mod 2 addition with 1 is 0, 0 mod 2 addition with 0 is 0. So R2 is 0, R1 is 0 and R0 is 1. So this is the actual data to be transmitted. But all of a sudden, because of some reason, the data which was transmitted was 011, 001. This is the data to be transmitted, but it was received a bit different at the receiver. And what was happened was, so there was an identified that the syndrome value instead of 000, it has been determined as 011. Okay, so what do you mean by this? So when syndrome value is not equal to 0, an error is present. Now to determine the position of error, you have a simple table which is shown here. Syndrome, if it is 000, it indicates there is no change in the data received. But if it is other than 0, so we have 7 other possible combinations, which is 001, 010, 001, sorry 011, 100, 101, 110 and 111. So depending on the value of the syndrome that is being generated, we can determine the position of error. For instance, if I got an error syndrome value as 001, it means the bit error generated was at position Q2, Q0. Because what was the received data that we are expecting to be represented as? B3, B2, B1, B0, Q2, Q1 and Q0. Okay, so if your syndrome value is 001, then it indicates there is an error at Q0. So whenever you are identifying the position of the error, to correct the error, the simple thing is complement the existing value. For instance, I got Q0 as 1, then to correct the error, replace it with 0. If it Q0 is 0, to correct the error, replace with its complement 1. Okay, so depending on the syndrome value, for instance syndrome value I got is 101, means 101 the value of error generated was at position B0. So find out at which particular B0, if the bit was 1, replace it with 0, if bit was 0, replace with 1. But remember, your so-called Hamming code will only able to correct one bit position of error. But when there is more than one bit of error change, that cannot be corrected by your Hamming code. So the data transmitted was 1101,000. That was the received code word, which is not correct. So what happened is the syndrome is 101. So we can try to get the data correction, but if it is more than one bit, the data cannot be corrected. So our code called Hamming code cannot correct more than two errors. This thing need to be remembered. Okay, right? I hope this is clear. Let's go for the next one. Well, in the previous slide, we were talking about an error correction code called Hamming code, which is basically a linear block code. We have another type of linear block code, which is special property called cyclic codes. What do you mean by cyclic codes? A cyclic code is a linear block code in which if we are cyclically shifting that particular code word, it is going to generate you a one more valid code word. So you have a code word, if it is cyclically shifted, then it results into one more valid code word. Let me make you people understand with a simple example. The set of code words are 0, 0 0 0 0 1 0 1 0 0 1 1, and next we have 1 0 0. Now look at 0 0 1 in case if the one bit is cyclically shifted, that is it is moving from the last bit position to this particular position. This process is called cyclically shifting. And what happens if your 1 is cyclically shifted to the first position? Now this will occupy the first bit, 0 moves to the next bit, and this 0 moves to the next bit. Now what is the ultimate value generated? 1 0 0, which is actually a valid code word. So if a code word is cyclically shifted and that results into another valid code word, then you call those kind of linear block codes as cyclic codes. So this is what we are going to discuss in this topic. In this, we are going to discuss the topics like cyclic redundancy check. How do you implement cyclic redundancy check for polynomials? Then what do you mean by cyclic code analysis? What are the advantages of adapting cyclic codes? And last but not the least, what do you mean by checks? So we are going to discuss this topics under cyclic codes. Cyclic code, a linear block code with the property that if it is cyclically shifted, it results into another valid code word. Here is an example of a cyclic code where a code word, for instance, 0001011, you are cyclically shifting this particular code word. So it will be moving to the first bit position. Then you will have 1 0 0. So on cyclically shifting, the code word generated is 1 0 0 0 0 1. Do we have that? Just check out here. First we need to have 1 0 0 0. Yes. Then 1 0 1. Okay. So or you want me to show it here? Right. If it is shifted to the first bit, it becomes 1 0 0 0 1 0 1. This is the resultant cyclic shift code, and just verify if you have this valid code word for another. No? Yes, here we have the same code word existing for a data word 1000. The code word is 1000101. So similarly, not only this, if you take any other example, for instance, if it is 0011101 and you shift it here, it becomes, for this case, 1 0 0 1 1 1 0. So just check out, for 1001 110 is another valid cyclic code word. So this property is called cyclic codes. Okay. So here you have an example of a data word of length k equal to 4 and n equal to 7. So the number of redundant bits added are n minus k, which is equal to 3. So a cyclic code, if a code word is shifted, cyclically shifted, it will result into another valid code word. Okay, right. So here n equal to 7, k equal to 4, and number of redundant bits are added as 3. Okay. So this is how we will get valid set of code words. Right. In the previous slide, we were talking about how a code word is generated for a given data word. Let us look at the procedure. How do we generate the redundant bits for the given code word, sorry, for the given data word, and how we are going to generate the code word from that. Okay, right. Let us first try to assume the data word which we would like to transmit is referred as A3, A2, A1 and A0. Now here the n is equal to 7 and k equal to 4. Now how many redundant bits are required? 3. So we are representing those redundant bits as R2, R1 and R0. So initially what we make an assumption here is we will take those R2, R1, R0 values as 0, 0, 0, and we will initially accommodating those three values along with A3, A2, A3, A2, A1. This is how we try to accommodate A3, A2, A1 and then A0, and we all redundant bits are taken as 0, 0, 0. Now, an additional input which we require in cyclic redundancy check to determine the redundant bits is we need a divisor. So we are along with the data word, we will be provided with a divisor with initially values assumed as D3, D2, D1 and D0. Okay, so this is a major difference between Hamming code and the device and cyclic redundancy check. So once a divisor is known, once we append the redundant bits zeros to the actual data word A3, A2, A1, A0, then we start doing modulo 2 division of this particular variable with the device. And on implementing of the division, modulo 2 division, we are going to generate the values for R2, R1 and R0. So these R2, R1, R0 along with A3, A2, A1 and A0 will be referred as the code word, and this is going to be transmitted to the receiver. Now here these variables are referred with the names B3, B2, B1, B0, Q2, Q1 and Q0. Now whether the data is transmitted as it is or there is any error in the transmission can be identified by forwarding this received data to a checker circuit, and here along with this values we are going to use the divisor, and again we are going to implement modulo 2 division. The remainder which is generated from the modulo 2 division of the received code word with the divisor is called syndrome S2, S1, S0. Like in the previous case, if the syndrome values S2, S1 and S0 are 0, 0, 0, it means there is no error generated. So whether the syndrome is 0, 0, 0 or other than that will be decided by decision logic. If it is 0, 0, 0, remove the redundant bits Q2, Q1, Q0 and forward the data as A3, A2, A1. If a syndrome is not equal to 0, 0, 0, then we are going to discard the data. Okay, so first we need to take a data word and determine the number of redundant bits. Assume initially the values are 0, go for a modulo 2 division, and after the remainder is generated, replace the 0, 0, 0 with the remainder value generated. And now the code word which is generated will be transmitted to the destination. At the destination, this received code word is forwarded to a checker circuit, and here we will use the same divisor which we have used at the transmitter. And now again after implementing modulo 2 division, the remainder generated will be referred as syndrome. Now the value of the syndrome is forwarded to a decision logic, and if the syndrome value is 0, 0, 0, it means the data received is correct, and we'll try to remove the redundant bits and forward the data. If syndrome value is not equal to 0, 0, 0, then the data code word will be discarded. Let us see a simple example to understand this particular cyclic redundancy check implementation. Right. Here, the data word which I am going to transmit is referred as the considered data word considered was 1001. So this is a 4-bit data word. So the number of redundant bits will be 3 and total length of code word will be 4 plus 3, 7. Now the divisor which we have in this particular example is 1001. 1 1. Now, before we go for the division process, what are the things that we need to remember for modulo 2 division is 0 minus 0 or 1 minus 1 is also called modulo 2 subtraction. Both of them will be generating 0, and 0 minus 1 or 1 minus 0 is equal to, in both the cases, the difference value is equal to 1 irrespective of the borrow which we are considering. Here we are not talking about borrow, only the difference is what we consider in modulo 0, modulo 2 subtraction, which is used in modulo 2 division. Right, let us start with this particular example. So the divisor is 1011 and the data word is 1001. So initially we are assuming the three redundant bits R2, R1, R0 as 0, 0, 0. Now start implementing modulo 2 division. 1001, 000 and divisor 1011, first the coefficient is 1. So it generates 1011. Now the modulo 2 subtraction, 1 minus 1 0, 0 minus 1 1, 0 minus 0 0 and 1 minus 1 0. So just ignore the first one. Now we are left out with 0 1 0, then we are getting the 0. Since the first bit is 0, so we are putting the next coefficient element as 0. So it will be 0 0 0 0. And again modulo 2 subtraction, 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 0 is 1. Next get the next 0. First bit is 1, so you put the coefficient bit value as 1. So 1 0 0 0, 1 0 1 1. Use these rules. 1 minus 1 0, 0 minus 0 is 0, 0 minus 1 is 1, 0 minus 1 is 1. So we have 0 1 1 1 and finally get the last R0 value here, 0 1 1 0. First bit is 0, so the coefficient bit will be 0. And again this value is all zeros. Now implement the modulo 2 subtraction. So the remainder that is generated is 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 0 is 1. So the remainder is 1 1 0. So the R2, R1 are not generated at the transmitter end for the data word 1001 and using a divisor 1011 is 110. So replace 000 with 110. This is the code word that we are going to transmit to the receiver. Now I hope you people have understood how that particular code word is generated. Let me just now the code word generated was 1001 110. Now if it is transmitted as it is without any error, now this code word that is received is applied to the checker along with the divisor 1011 which was used at the transmitter. Again try to implement modulo 2 division, and now when you implement a modulo 2 division for this case, initially the first bit is 1 out of 4 bits, so we'll have a coefficient 1, so 1011 and modulo 2 division subtraction, 1 minus 1 0, 0 minus 1 1, 0 minus 0 is 0. So get one more here, 0 1 0 1. The first bit is 0, so put the coefficient bit as 0. Next we have 101, then get down this one important, 1011. Now the first bit in this value is 1, so take the quotient bit as 1. Now we will have 1011 and all the remainder bits are 0, and this 0 is brought down, and totally since the first bit is 0 we will have a quotient bit as 0 and totally the syndrome value is 0. Remember, whatever the code word that was transmitted was received as it is without any error, so syndrome value is 000. And we have discussed in the previous slide, if syndrome value is 000, the correction logic, the decision logic will forward the data by removing the redundancy bits. So in this the redundancy bits 110 is eliminated and only 1001 will be transmitted to the forward. In case if one of the bits which is received in the code word has got corrupted as 1000110. So here, let me just try to, here there's a small change. So 1001, this is changed. So instead of 100, so there is a change in one of the bits of the code word. And now when you implement the modulo 2 division, initial first bit is 1, so 1011, the quotient bit is 1. So implement the modulo 2 subtraction, 0 minus 1, 1, 0 minus 1, 1, 0 minus 0 is 0. Get this one down. So here it will be, once again the first bit is 0, so the coefficient bit is 0, 0, 0, 0. So you will have 1, 1, 1. Get down the 1 by. Now we again the coefficient bit is 1, so 1, 0, 1, 1. Implement the modulo 2 division and we will get 1, 0, 0. Last bit is brought down and the first bit coefficient is 1. So again coefficient is, so here you will have final remainder as 0, 1, 1. A small correction here is the coefficient bit is 1, 0, 1, 1. Okay. Now you could find that syndrome value is now 0, 1, 1, which even forwarded to the decision logic immediately rejects it because it is not equal to 0, 0, 0, and the data word will be discarded. This is how a cyclic redundancy check will be implemented. So we'll discuss, I hope this problem is clear. We'll try to practice one more problem in the next class and we'll try to complete a discussion on cyclic redundancy check, and we'll also have a look at the last method of error detection and correction called checksum method. We'll meet in the next class.